Well, there are some limitations of finite state machines. Okay, there are some limitations of finite state machines. So, what are the limitations? We can say that is impossible to multiply. Okay, so you can say that point number one, it is impossibility of multiplication. So we have seen that a finite state machine cannot remember arbitrarily long sequences. We have seen that. Okay, so and we know that during multiplication operation it is required to remember two full sequences corresponding to the multiplier as well as the multiplicand. Okay, so moreover, while multiplying, it is also required to store the partial sums. Okay, because in each state you will get the partial sums that are obtaining during the intermediate stage, which I already told you. So therefore, finite state machine cannot multiply. Okay, for a given two arbitrarily long numbers. So because only that finite state machine does not have any memory. So intermediate result it cannot store because there is no possibility of storage in finite state machine. So it is impossible to multiply two numbers. Okay, so this is one problem for one of the limitations for finite state machines. Another problem or another limitation of finite state machine, you can say that palindrome recognition. Okay, so palindrome recognition. So, finite state machine is also cannot recognize palindrome string because it does not have the capability to remember all the symbols it reads until the halfway, because you know the palindrome half portion is one symbol and another half is the reverse of that symbol. Okay, and hence it cannot match them in reverse order with the symbols in the second half of the sequence. Okay. For palindrome recognition, finite state machine cannot work. Okay. Also, it cannot check the well-formed parentheses also. Okay. So you can say that impossible to recognize well-formed parenthesis. Means suppose this kind of parenthesis is given, or this kind of parenthesis is given. So this is a well-formed parenthesis. So here also you need a something storage memory to remember. So since the finite state machine do not have any storage memory, so it cannot remember all these thing. Okay, and to check to recognize a well-formed parenthesis. So these are the limitations of finite state machines. We need some more powerful machine to recognize this kind of activities. Okay, so since the finite state machine is not so much powerful, so our powerful machine which can recognize all these things are needed. Okay. So what are the properties of the powerful machine which can recognize all these things? So you can say that number one, I can say that finite state control similar to that finite state machines. Okay, since any program need a finite number of functions. Okay, so number one point, you can say that finite state control similar to that of finite state machine, since any program needs a finite number of function or states. Okay. And what is the number two? You can say some external memory capable of remembering arbitrarily long sequence. Okay, long sequence of inputs. To achieve this, the state should have unbounded one directional memory form which can choose any required part by moving left, right, or staying in one position. Staying in one position means there will be no movement. Okay. The entire unbounded tape acts as infinite memory. That is, you can say that there will be one tape. Okay, and here there all the symbols will be there, and there will be a tape pointer header which can move either this side or stay idle. Okay, So we will study that, what is basically mean. When we will study this, you can understand more clearly. Okay, so this is the second point. Now, third point, you can say that ability to store or write onto the tape. That is, you can store, this is a tape, so you can either store or you can write into the in this tape. The machine head, this is a machine head, okay, this arrow sign should be read and write head. It is will act as read and write head. That is, it basically either it reads some symbols from this particular block, or it can write symbol into this particular block. Okay, so this is the third point. Another point, you can say that ability to consume its own output as input during execution at a later time. For this, all the intermediate information must be stored in the memory. Okay, so where we can use this just for multiplying the numbers. So while multiplying the numbers, the multiplication is a process of division, addition, you know that. So for the multiplying numbers, it is required to store the intermediate or partial sums, because you know when you multiply, there are partial sums is generated, which are added later to the final answer. You know that. That is the main basic features of the multiplication. So hence this distinction between the input and output symbol need to be dropped. This means that external communication as well as communication within the machine should rest on as a common alphabet set. Okay. So these are the 4 points. We need these 4 points which can should be there inside you can say a new machine. Okay, so all these characteristics are combined into a machine that is called Turing machine. Okay, and the Turing machine satisfies all these 4 points, and it is proposed by Mr. Alan Turing in 1936. Okay, so we will study now this Turing machine now. Okay, so it is a very important thing, Turing machine, and it is the most powerful machine. It is more powerful than finite state machine or push down automata, and it generally accepts the type 0 grammar. Okay, so any kind of grammar it is accepted is the Turing machine. Now we will study this Turing machine. Okay, so what are the elements of the Turing machine? So first we will discuss what are the elements of the Turing machine. So let us draw one figure. So like this, I'm just rewriting this figure. So this is one kind of tape, you can say that. So there are some, this is a symbol 0, this is symbol 1, A, you can say B, 1, 1, and this tape is infinite in both the ends. Okay, so these are all what you can say that these are all string tapes. String tapes. Okay, so these are all the string tapes, and so this is the read write header. You can say this is right. This, if it goes right side, so this is the right, this is the left. Okay, so this is right, this is left, and this is nothing but this is nothing but read or write header. Okay, and these are all the blank tapes. Okay, so these are all the blank tape. Okay, and this is also the blank tape. Fine, and this is the read write header. So this is, you can draw like this way. This is the state, and this part is finite control. Okay, so this is a pictorial diagram of Turing machine. Okay, so it is a pictorial diagram, just a simple sketch of the Turing machine. Okay, so these are the elements. So what are the number 1 elements we can see? There is a head. This is a head. Okay, this is the head. So a head which can read or write a symbol at a time and move either in the left direction or in the right direction, or remain in the same position depending on the symbol read from the tape cell. These are all the cells. Okay, these are all the cells. These are all the cells, and these are all the symbols inside the cells. Okay, so this is a head which can read or write a symbol at a time and move either to the left hand side or right hand side, or stay or remain in the same position depending on the symbol read from the tape cell. Okay, so this is number 1 point, and now we will study this tape. Okay, so this is an infinite tape. Okay, it can extend on the either side of the head. Okay, mark into the small squares, okay, on which the symbol of the alphabet are written over here. Okay, this tape represents the unbounded one-dimensional memory, which is considered to be filled with blank characters. Blank characters means here the symbols may be the blank, and we will write like this way, or anything. I write this small b and cross it, or sometimes I can write capital B or crossing, or phi, whatever notation I use. Okay, so these are all the blank characters. So again, what is this? This is nothing but an infinite tape extending on either side of the head, okay, marked off with the square cells, on which the symbol from the alphabet, can be written. Okay, the tape represent unbounded one-dimensional memory, which is considered to be filled with blank characters unless and otherwise stated. Okay, and this is number 2. Number 3, you can say that a finite set of symbols called the external alphabet set, which is represented as I. Okay, which consists of lower English case letters, digits, usual punctuation marks, and the blank character. Okay, so third point is a finite set of symbols which is called external alphabet set I, which consists of lowercase English letters, digits, usual punctuation marks, and a blank character, this. Okay, so this is the third point. And number 4 point, a finite set of state denoted by capital S. Okay, the machine normally reside in one of these states. Okay, so this is the 4th point. So we can see that the Turing machine overcomes all the limitations of the finite state machines. It has an infinite memory. This tape is infinite in both directions. So it has an infinite memory in the form of a tape that is unbounded at the both ends. Okay, because it is unbounded two-way. There is a read-write head that can move in any direction. And helps the machine retrieve the information from the tape that is stored earlier. In a way, this can be considered as converting the dumb storage into the memory. This is a dumb storage. Initially it was blank, so you can store something. So you can say that it can consider as a dumb storage into the memory. It can consume its own output. If you write something, it can consume its own output for later use. In the algorithm execution. Basically we will use in multiplication operation or some calculations. Okay, so these are all the features make the completely powerful machines. Okay, so we can say that the Turing machine and finite state machine are too extreme. Okay, Turing machine and finite state machines are two extreme machines. So finite state machine, you can say that is a minimal machine, and whereas you can say that the Turing machine is the most powerful machine. Okay, so these are the basic things of the Turing machine. Okay, so let us now define some definitions. Okay, Turing machine, we have already said that the Turing machine, I will write as TM, capital TM. It has a finite set of symbols I. Okay, it has a finite set of symbols I and a finite set of state, capital S. Okay, of which one of which is halt or final state. Okay, one of which is either halt or final state. Okay, either halt or finite state. So a Turing machine is denoted with the help of 3 functions. Turing machine can be denoted with the help of 3 functions. Okay, so what are the functions? Number 1 is the machine function. Okay, machine function or MAF, and it is denoted as MAF. We can write like this format: I into S, I, S, it will generate I. Okay, so and number 2 is state transition function. Number 2 is state transition function, or STF. Okay, so STF you can write like this way, I into S, it is S, and number 3 is direction function. Number 3 is direction function. Okay, and you can write this as I into S, it turns to D, basically generate D. And what is D? It is either left, it can go moves to the left or moves to the right, or it may stay idle at same position, so it is a neutral position. Okay, so you can say that L means move towards left by one tape cell position. Okay, L means move left, move left. Okay, move left by one tape cell position. L means move right, one tape cell position, and N stands for no movement or neutral position. Okay, that is it will stay in the same position and remain at the same tape cell. Okay, which can be read last. Okay, so these are the basic three functions. And next we can say that based on the Turing state, which is an element of S at a given time, and the input read symbol, which is an element of capital I at any given time, the machine either takes no action or perform the following three actions. Okay, so it can perform the following three actions. So let us see what are the following three actions. The input symbol is erased and another symbol is printed on the tape of the cell. That is, input symbol might be erased and another symbol can be printed on the tape cell. Okay, this is number one. Number two is that the internal state of the machine is changed. That is, state you are from Q1 and you can go to the Q2 state. Okay, and number three, the head either moves one cell towards right or left or remain in the same position. So these are the three actions can be taken. Okay, so in the next we will study what are the tuples of the Turing machine. Basically, you will see that there are seven tuples. Okay, so we will discuss elaborately what are the tuples. Okay, so just I am writing, it is Q, capital Q, which is the finite set of states. This is a summation sign. Okay, it is the set of input symbol, which is the subset of some tau. Okay, it is a subset of tau. What is tau I am defining? Which is exclude the blank characters. Next is this tau. This is a new symbol I am introducing. So it is nothing but a finite set of allowable tape symbols, including the blank characters. Okay. Next is your small delta. Okay. This is a functional matrix, and we will see what is the delta elaborately. Next is your Q0. Q0 is nothing but it is the start or initial state, we know that. And next is capital B. So it is a blank, is a symbol for blank character and denoted normally by this sign. Okay. Next it is the F, capital F. So what is the F? F is the finite set of final state. Okay, or whole state. Okay. So we will study each of these elaborately. So let us just begin with this. So we can say that what is Q? Q is nothing but you can say that finite set of state. Now these are very important for exam purpose. This tau is nothing but you can write finite set of allowable it is okay, allowable tape symbols So finite set of allowable type symbols, including the blank character, including blank character, this one. Okay, and this is a summation sign. It is nothing but, you can say, the set of input symbols. Now it is nothing but which is a subset of tau, which is a subset of tau, but excluding, okay, excluding blank character, blank character. Okay, now B, as usual, symbol for blank character, okay, and denoted by like this way. Q0, as usual, you know that what is Q0. It is a start or initial state. It is start state and it belongs to capital Q. Now F, what is F? It is a set of final state or halt state. So these are all important. You have to remember all this, because this they will give the description, they will ask you the question, what are the 7 tuples of Turing machine. So F is nothing but set of final state or halt state, which subset of is a Q, and this is important, the functional matrix, functional matrix, such that, now this is a mathematical term I am using, you have to remember that Q cross tau, and it will generate what? Q cross tau cross left, right, neutral. Okay, so this one. So these are all the 7 tuples, and each of the description I have just shown to you. So these are the 7 tuples of the Turing machine, and each of tuples has been described over here. So this is basic things of the Turing machine. That is, finally we can conclude that a Turing machine is a, you can say that it is the most powerful machine that accept the type 0 language of Chomsky grammar. Okay, you know that there are 4 types of grammar, type 0, type 1, type 2 and type 3. So it accepts all kind of grammar, and whatever computer can solve, the Turing machine can solve it. Just one point to remember, before the computer has invented in 1936, Alan Turing has given the description that someday this machine will generate, which nowadays computer is generating this. Okay, so there are still now no problem is there which cannot be solved by Turing machine. Okay, rather I could say that still now no computer has been generated which can solve some problems which cannot be solved by Turing machine. Okay, so we will go for the problems based on the Turing machines in the next videos. Thank you.